Hello people, welcome back to your Anime 101 course. Through this tutorial, we will learn to create more complex behaviors using particle systems we already set up. We will try to generate swarming systems. There are two methods in order to achieve this. One is the metric distance model, where we evaluate the distance between one element and all the neighbors, and there's the topological distance model, where we evaluate the distance between one element and say 6 or 7 neighbors, which we can actually establish on Grasshopper. So let's get started. First off, we need to create a point cloud, a random point cloud. I will use 50 points, and I will calculate the masses of this element, this length. We'll use random masses again. Random numbers. Construct domain. There we go. So we'll use equal masses for this simulation at the moment. Okay. Now I need to set my global acceleration. Let's go to 1 at the moment. Global accel, and we need to establish a translation vector. Second vector, I will go by unit y. Next, we need to create Newton's second law of motion. So let's write it down just like we did on the last tutorial. Length of the force divided by mass multiplied by the unitized force. Okay, let's rename our inputs. The force equal the mass, and calculate the force and the mass. There we go. After that, let's begin our loop. Loop start, loop end. We need additional inputs here, just one, and then right click record data. Okay, data will be the points, and D1 will be the translation vector. Okay, so yeah, this connection, and I will double click this. Okay, put it off. We'll calculate the say 6 neighbors for each point. So I need to calculate the closest point for each of these. Right click flat graph, and the point cloud will be the same one. And I need to establish the number of neighbors. I want 6, but since I am using the same point cloud, I need to increase it by 1 so I get an extra point, and then I remove the current one. Call index. I need to remove the very first closest point, which is the same one. There we go. After that, we need to create a vector, 2 points. We'll graph this input from each of this point to its neighbors. Right. After that, I need to create the attract and repel vectors. First off, we need to unitize the vector. We'll create the attract vector first. We need a multiplication of the length of this vector by a multiplier, which I will use 2. This will be the attract acceleration. That will amplify this vector by its acceleration. Next, I need to reverse the vector and I need to create the repel vectors, which will be basically the same but using the reverse vector. Repel acceleration. Instead of using this unit vector, I will use this one, the reverse. There we go. So this is the attract and this is the repel. Now I need to create distance thresholds in order to swarm properly. So I will tell my system if the length of the original vectors is smaller than say 6. So I got a pattern which I will use to select whether to attract or to repel. So I can just pick and choose. The pattern will be this one, and 0 will be to attract vector, 1 the repel vector. There we go. I got my attract and repel vectors properly set up according to distances. So if the distance between neighbors is smaller than 6, we will repel, else we will attract. We need also to calculate an average vector, so we keep the average translation. So we need to go larger than, if the length of the vector is larger than the same number, we just the distance threshold. Distance threshold. If it's larger than, we will use a cull pattern for these vectors. Larger than, we will unitize. We will amplify by some number. 0.05 seems good. Okay. Now I need to make a mass addition of all the average and attract and repel vectors. Let's do a mass addition between all this and all this. And this is the final vectors of the swarming model. Also, we need to recalculate Newton's second law of motion using these new vectors. In order to do so, let's write eval. We need a new input, and we need to rename the inputs to force, to mass, and swarming, well, acceleration we'll call it, accel. And the expression will be, this time we won't divide the force by the mass explicitly. Actually we will. Let's write the function length of the force divided by mass times acceleration times the unitized vector of force. Okay, so which is our force? Is this one, the result of the mass addition. The mass will be actually the same masses. We need to flatten this output, the result of the vectors. The mass will be the same masses at the beginning, and the acceleration will be the global acceleration. This is where we recalculate. Oh, no, never mind. It's not the global acceleration. We did a new acceleration, which is the swarming model acceleration. We'll just put 0.01. Just blowing with my expression. Oh, mass, yeah. Okay. That's another problem. Acceleration, accel. Sorry. There we go. So this is the actual swarming vectors. Also, I need to recalculate the translation vectors using my global acceleration multiplier. So let's calculate the vector length of the translation vector and amplify it, multiply it by the global acceleration, which is this one at the beginning, and then amplify the vector by the new acceleration. So this is the new translation vector. Translation and swarming. I need to sum both the vectors. And this will be the resulting vector of translation. We will move the points, which is where is data? There you go. This is this one. So data goes into the result of that, and the translation vector will be the resulting one, which is this. We'll turn this off. We'll turn off the rest, and I will loop, say 20 times. There we go. This is a bundling, a swarming model. They are repelling and attracting each other based on the distances. They keep moving along a common direction. I can actually recreate a polyline using this point flip matrix or an interpolate curve. And we'll trigger the loop. There we go. So this is basically how it works. A basic swarming simulation using anime loops, which is quite useful for whatever you want to do. So that's it for this tutorial. Thank you all for tuning in, and see you in the next part of this course. See ya.